In this video, we will create a bridge between the abstract concept of the two-step floating catchment area method and a practical GIS workflow that analyzes pharmacy accessibility and staff distributions in Vermont, particularly in flood-prone areas. Recall the two questions motivating our work in this case. We want to understand, first, what is the geographic pattern of pharmacy accessibility in Vermont? And second, how did that pattern of accessibility change during the 2023 flooding events? We can answer these questions using the two-step floating catchment area method. Recall that the method works in two steps. First, we define a catchment area around each pharmacy, and this area represents the area a pharmacy can serve. We will calculate this area using drive times. The second step flips the perspective, looking at how many pharmacists are accessible to a community within their own catchment areas. To keep things simple, we will look at how community boundaries intersect with pharmacy catchments. However, we could alternatively create catchments for those community areas with varying sizes for each community. Let's move into the technical workflow. We start by preparing our data. First, we need to set up our study area. We want to study Vermont. However, think about the spatial processes we are measuring. Residents of Vermont can certainly access pharmacies within their state, but they could also access pharmacies in neighboring states. Similarly, residents living outside Vermont but nearby might access pharmacies inside Vermont. If we were to just use Vermont as our study area, we would miss these relationships, creating what is called an edge effect. To account for the possibility that some of these pharmacies serve populations outside of Vermont, we create a 40-mile buffer around the state boundary. This area is called a guard area because it guards against the problems created by edge effects. Combining this guard area with population data by finding the intersection of the guard area and the population data allows us to gather the data we need. This process allows us to capture the communities from neighboring states that rely on Vermont pharmacies and the pharmacies outside of Vermont that Vermont residents might rely on. With our study area and guard area selected, we next need to bring in data about pharmacies themselves. We have pharmacy location data and staffing information, which includes both pharmacists and technicians. Since pharmacists are considered more critical to operations and healthcare, we'll calculate a weighted service value for each pharmacy by adding the pharmacists plus 1/2 for each of the technicians to determine the total staff available at each pharmacy. With the pharmacy data and buffer set up, we can calculate the population serviced by each pharmacy using GIS. With our GIS, we create travel areas, 30-minute drive time polygons around each pharmacy, and summarize the population within these areas. This gives us a clear view of how many people can access each pharmacy. Once we have this information, we calculate the staff to population ratio. If we desired, we could calculate this ratio for different days of the week using the weekend, Saturday, and Sunday staffing fields. Not all pharmacies are open on all days, so this could help us quantify how many people have access to different pharmacies on different days of the week. We then take our analysis a step further and finish the two-step floating catchment method by summarizing the pharmacy-specific supply-demand ratios at the county subdivision level. This shows us how pharmacy accessibility and staffing resources are distributed across different areas in Vermont. We can also capture urban and rural areas by leveraging geographic data that identifies different sized towns and cities in the states. These steps give us the information we need to answer our first question: what is the geographic pattern of pharmacy accessibility in Vermont? We can make minor adjustments to this workflow to answer our second question: how did accessibility change during the 2023 flooding event? By incorporating data points of road closures due to flooding, we can recalculate the travel areas, this time using road closure points as barriers, and summarize how populations serviced by pharmacies are affected by road closures during the previous flood. While this is a useful analysis, consider also how it might underestimate actual changes in accessibility. What assumptions are being made in this workflow? For example, does the research design here treat all pharmacies as if they remained open during the flooding? Does it assume staffing levels remain the same? What does it assume about residents' ability and willingness to go out to seek out pharmacies during the flooding event? You will consider these questions and how your answers might impact your result later in the module.